A resolver is a very specialized transformer that measures angular position with high accuracy. We can explain how a resolver works in terms of the magnetic inductance of the various windings. The outside of a resolver looks like an electric motor, but the inside windings are that of a transformer. The stator has 3 windings, a primary one and 2 two-phase ones. The primary winding of the stator is excited by external AC current. Electromagnetic induction induces current in the first winding of the rotor. Because these windings are collinear along the axis of the resolver, the same current is induced in the first winding of the rotor, regardless of the rotor's angular position. Current then flows to the second winding of the rotor. Again, by electromagnetic induction, current is induced in the secondary windings of the stator, which are fixed at right angles to each other. Because of the orientation of the windings, the stator produces 2 alternating currents that are 90 degrees out of phase with each other, varying as the sine or cosine of the rotor angle. They are also sinusoidal in time, varying as the AC line voltage frequency. The stator windings repeat their spatial waveforms every full rotation of the rotor. And now for an even trickier part. The resolver is an analog device. We need a way to measure and digitize the relative magnitudes of the two-phase stator voltages so that we can back out the rotor angle. The relative magnitude of the voltages is the sine of the rotor angle theta divided by the cosine of the rotor angle theta. This product is tangent theta, and the angle theta is calculated by taking the arctangent. Commercially off-the-shelf resolver-to-digital converters, like one from Analog Devices schematically shown on this next slide, are available to do the math for you. The signals of the resolver are applied to cosine and sine multipliers with digital angle phi. The 2 resulting signals, V sine omega t sine theta cosine phi and V sine omega t cosine theta sine phi, are subtracted from each other by the error amplifier to give the signal V sine omega t sine theta cosine phi minus cosine theta sine phi. Using the trigonometric addition formula shown in our slide, remember trigonometry? The signal is equal to V sine omega t sine of theta minus phi. This error signal, sine of theta minus phi, is fed through the rest of the system so that the counter's digital output phi represents the angle theta. If you want to know more, refer to the Analog Devices reference material in your homework reading for more details. And now it's time for some resolver details. First thing to remember is that the better resolvers are brushless. Unlike a motor, however, a resolver does not have to drive a load. It's only a sensor. Hence, the input voltages to the static primary winding is usually less than 26 volts AC. Industrial-grade resolvers are designed around the 50 or 60 Hz AC power commonly available in factories. Resolvers for marine or aviation use are designed around 400 Hz power supplies. Military-grade resolvers may go as high as 12,000 Hz. And recall that resolver-to-digital converters run the signals on the stator secondary windings through an error amplifier. This has the advantage of canceling out noise injected on both windings. A little more about resolvers. The resolver-to-digital converter electronics is normally not purchased with the resolver, nor is it mounted directly to it. Here's the good news. Your electronics will be kept away from the harsh environment that the resolver experiences, particularly for temperature and RF interference. Now here's the bad news. You're normally going to have to deal with 2 different vendors if you're designing a system, and you need to make sure their equipment plays nice together. You can get higher resolution and thus higher accuracy if you purchase what's called a multiple speed resolver. A multiple speed resolver with 2 N pair of secondary windings will deliver N cycles of sine waves in 1 mechanical turn of the resolver. The resolver will then be N times as accurate. For example, if N equals 8, your stator will have 16 sets of secondary windings. It will deliver 8 full signals in 1 mechanical turn of the rotor. Your resolver will then have 8 times as good accuracy as that of a single-speed resolver. And now we highlight issues with resolvers. First warning is that multiple speed resolvers do not understand absolute position. With a 4x resolver, for example, a nominal output of 10 degrees clockwise could really represent 10, 100, 190, or 280 degrees. So if you want to also know exactly which of these 4 possibilities represents your absolute position, you have to mount a single-speed resolver in series on the same shaft. Your cost just doubled. A resolver normally requires an external resolver to digital converter circuit. And you can buy a digital resolver which has this circuit included, but then you can't place the resolver in nearly as extreme a temperature or vibration environment. Like most instruments, resolvers have trouble outputting a 0 signal. In this case, you typically get 0 offset of 10 to 40 millivolts due to imperfections in the secondary windings. This slide shows the typical construction details of a resolver. This model has a mounting plate to attach to the structure that holds the motor. There is also a round metal cover for EMI shielding. The resolver shaft will be coupled via flex coupling to the motor shaft. Rugged bearings support the rotation of the shaft inside the rotor and stator windings. The small circuit board has some programmable switches for optional user settings, and the back plate holds a pin and socket plug popular in aerospace applications. Once in position, you can easily think that resolver is an electric motor. Let's recap. We took a deep dive into the electromagnetic theory governing resolvers and some construction details of these rotary sensors. Now let's review applications for resolvers, as well as how to specify and integrate them into your electronics.